Hi everyone, welcome to our presentation. This is Feng Huang from HK PolyU. Glad to be here to present our work about Coarse-to-Fine LiDAR-based lens with dynamic object removal in dense urban areas. The author including myself, Feng Huang, Mr. Sun, Dr. Wen, Ms. Zhang, and Dr. Xu. So, what is the challenges of LiDAR lens? Before answer the question, so let me introduce a little bit about what is LiDAR SLAM first. So SLAM is short for simultaneous localization and mapping. It is fundamental for most autonomous systems. The LiDAR can provide a dense 3D point cloud of surrounding by measuring the time of reflecting light to the receiver. Most of the SLAM method is rely on the static world assumption, which means that the ideal world is static. So you can find an optimal transformation by minimize the distance of correspondence. So let's check out an example of the light urban. The vehicle is static, the house also static too. So, how's the performance of a LiDAR stand in urban areas? So you can see we still have the house, right? The high-rising buildings. But we have more about the dynamic object, the pedestrian, the vehicles, and the bus, something like that. So we can show you a more example of the urban chaos in Hong Kong for your attentions. So you can see it's a busy crossroad here. So, but how's the performance of the LiDAR stand in such areas? According to our previous work on benchmarking LiDAR stand based on the urban chaos, the theoretical difference of the state-of-the-art LiDAR odometries are analyzed here. So we have analyzed the point modeling, the data association, and the cost function here. And we also evaluated the publicly available LiDAR scan algorithms. We are running on Rose Melody under Ubuntu 18.04. So the code setting is over here. The evaluation results shows that long outperforms others measures in terms of cost efficiency and satisfactory position accuracy. Therefore, we chose the long for the baseline for our proposed measures. So even for the state-of-the-art long, the performance still degenerated by various dynamic objects. We have done experiments before. The y-axis is the percentage of dynamic object. The axis is the epochs. We can see the long also affected by the dynamic object. So for example, for the epoch 325, the dynamic object goes up, and also translation is also become larger. Also for the epoch 400, so if a car and a bus nearby, the translation error is also going up. So we can conclude that the dynamic objects are the changes for long. Furthermore, we can check out an example of a car go through a crossroad with numerous vehicles surrounding. So as a result, the LiDAR mapping is not clear due to dynamic points is remaining in the point cloud map. To summary art, the dynamic objects is very changes to the LiDAR scan. Many literature are working on the dynamic object removal in 3D LiDAR. A research team proposed a Model 3 detector based on the discrepancy between the scan to previous scan. So another Sumo++ is proposed by Chen in Aeros 2019. The dynamic object is removed by segmentation based on deep learning method, RangeNet++. So another method proposed by King in Aeros 2020, visibility check between the scan to submit based on the range image. However, the performance of the detection and the motion estimation in a highly urban areas such as Hong Kong is still a changing research topic. There are numerous dynamic objects in the dense urban canyons, so if we didn't remove them, they will remain in the mapping result. So we implement object detection method based on the PVRCNN, so we can detect the dynamic objects. So after that, the mapping result is clear with the dynamic object exclusion. So our objective is to propose a coarse-to-fine LiDAR-based pipeline with the dynamic object removal. So in our experiments, the reality translation is improved 19% by filtering the dynamic object and the coarse-to-fine process, and also a cleaner polychromat is generated. There are three parts in our proposed coarse-to-fine pipelines. The first part is the dynamic object detection. We have several scan and a notated label. So we put it for the PVRCN for the training. So after the training, we can get a custom train models. So the point cloud will go through the PVRCN network with the custom train model. So we can get the instant labeled point cloud. So in the coarse LiDAR strand stage, we have a long here, so we can see we can state estimation, so we can get the point cloud with the pulse. After that, so the pulse can accumulate into a submat, so we can implement a range image-based scan to submat to visualization check the difference between the scan to submat to further refine the dynamic object removal. So finally, we have long in the 5 stage. He can output the refined polychromat and the accurate pulse. So let's invite Mr. Shen for the first part, the dynamic object detection.
Okay, thanks Huangfeng for his introduction. I'm Donghui Shen. I'm going to introduce you the 3D object detection part of our task. The first part of this task is data annotation. We used an open source data annotation tool named Sustek Points to annotate our data, and we annotated part of our data for the training of the model. The framework we're using for 3D object detection is called PVRCN. This is an algorithm which followed the structure of traditional RCN. It consists of the region proposal module and the refinement module. It used 3D voxel convolution as a backbone for feature extraction and high-quality 3D proposal generation. In the meantime, the features of different scales during the 3D sparse convolution procedure will be saved and used in this voxel set abstraction module for better point-level contextual capturing. By deeply integrating the two types of neural networks, it will lead us to more accurate and efficient 3D object detection. Let me show you some results on our testing set. The green bounding boxes are showing as detected vehicles. As we can see in both harsh urban and medium urban scenarios, most cars are well detected. Okay, this is the end of the 3D object detection part. Let's hand over to Huangfeng.
Let's come to the second part, the long. It's short for LiDAR dometry and mapping. If you come to the first feature extraction, if you extract the edge and the panel point based on the smoothness of a small region near to a. So which means that if you have a structure like this, the smoothness is small, so means that is a panel point. So if it's an edge point, like this one is the edge point, the smoothness, the C value will be large than normal one. So we can show an example running on our data set. something like this one is edge, and the ground is mostly is panel points. Okay then, so we will calculate the ratio between the point to line ratio, the current k+1 scans the edge point. Then he will calculate the ratio between the previous scan, the ji, the two nearest point. So we also calculate the point to panel ratio. Yeah, we found a panel point to find 3 point the nearest point by kdj of the previous scan. So the ratio also to carry the ratio also. So our target is the optimization part is to minimize the ratio of the feature points. We can use the LM method to optimize that. Long is used in both coarse and fine stage. In the coarse stage, they are used to construct submaps. Submap means the surrounding map based on the current pulse and also provide initial guess to fine stage. In the fine stage, it can refine the final point cloud mass and accurate pulse is generated. So the third part is the range image based scan to submap. So we can have the consistency check between the scan to submap, so we can further refine the dynamic object. So the dynamic object is further refined by the calculator difference between the range image of the scan and submap. First, we project the current scan SK into the IK, also SKM to the IKM. So we calculate the differential map between that. The red indicate a higher discrepancies between the current scan to the map. So if pixels have a larger than certain threshold, so we mark it as a dynamic one. So we later then the scan reading in the submap we further refine by the pointwise dynamic labels. But we also know that we will have some false labels with clustering and the drivable area variation to further filter the actual dynamic points here and here and here. We conduct our experiments with the OpenNAV dataset. The OpenNAV dataset is collected from various degree of urban areas in Hong Kong and Tokyo. The dataset contains measurement from the GNSS, IMU, camera, and LiDAR. Because besides the ground truth is recorded by the span CPT, which integrate GNSS RTK with fiber optical gyroscope levels of IMU, so it's very precision. So our conduct our experiments in pilot data, so it's the OpenNAV HK data 2019 04 2028. We use around 300 frames for training and 100 frames for validation. All the frames are used with detection resource are further processed by Long. So we reach an IOU of 69% in the dense urban areas. IOU is the intersection areas divided the union areas. In trans 3D, we reach about the 67% for the AP 0.5. In terms of positioning resource, first we have some dynamic object, notated. You can see the percentage, and the percentage is the dynamic object is quite up and down in some cases, and the long C. Long C means that the long with the cost process, the PVRCN is used to detect the dynamic objects. So we can see the long C have some improvements in some scenarios, such as the A, B, and C. So The overall performance compared to the long and long C, you can see the long C is the IMSC is decreased to the 0.364 compared to the original 0.45. So you can see we have an improvement of the 19%. We also have some case study for the 3 cases we mentioned previous in the EPO around the 220 and the 320 and around 14. We also conduct a Coarse-to-Fine process for the with the further refined by the discrete of the scan to submit, also the initial guess. You can see in the case 1, the long C is better. So in the case 2, is long CFA is the better, and some other place we can overall in the percentage result is much better than the original long. The mapping result shows that before the dynamic object removal, the dynamic vehicles will remain in the mapping resource. So after dynamic object removal, the most of the dynamic objects are removed. Is that some of the residual is due to imperfection of the object detection. Another mapping resource shows that before then we have some dynamic object here, so we already exclude the dynamic object, but you can see some maybe the pedestrian is also exist, so we need more class of dynamic object. We currently will change the vehicle type in this work. So we come to the conclusion. First one, we present a completed pipeline for the Coarse-to-Fine LiDAR-based pipeline with dynamic object removal. We can also see our improvement for 90% in denser urban. So we also combine instant levels deep learning measure, also the pi-wise discrepancy calculation to deal with the dynamic object. So finally we can able to construct a better cloud match to represent the real world in urban areas. So feature world, in terms of the feature world, we will because currently we use the manual labeling. We also want to start to train a supervised or unsupervised neural network to support more dynamic object type in urban areas. So we also figure out that if we just exclude the dynamic object, they will have some artificial potential power. So we will weigh the dynamic points for state estimation, make it more stable. So we also like to evaluate the performance under diverse urban areas. We recently open source UrbanLife dataset, which is data collected from various degrees of urban from Hong Kong and Tokyo. Welcome to check out and try it on download and join us for the research. Thank you for your attention. If you have any questions, please feel free to contact me through email. Thank you.